There is a machine right now, this second, sitting 13 billion miles from where you are reading this, doing something that no other object built by human hands has ever managed to do for this long. It is not the famous one. Everyone knows the famous one, the one carrying the golden record, the one that gets the anniversary specials and the documentary narration, the one that became the first human object to reach interstellar space back in 2012. That is Voyager 1, and it deserves every bit of the attention it gets. But it has a twin. Launched 16 days earlier, moving through an entirely different slice of the sky, carrying an instrument its more famous sibling lost almost half a century, HAGO. And because that one instrument kept working, this quieter spacecraft did something in 2018 that its own twin, for all its historic firsts, was never actually able to do. It measured interstellar space directly as it crossed into it, with a working sensor built for exactly that purpose. And what came back did not simply agree with what Voyager 1 had suggested 6 years earlier. In several important ways, it upended it. Right now, in the summer of 2026, that same spacecraft, Voyager 2, is at the center of the riskiest engineering gamble either Voyager has ever faced. A power-saving maneuver so drastic the team building it started calling it the Big Bang, and everything about how much longer either spacecraft survives may come down to whether it works. Stick with me, because this is the part of the Voyager story that rarely makes it into the headlines, and understanding it changes how you look at everything that's about to happen this summer. Start with the launch dates, because the numbering trips people up every time. Voyager 2 went up first on August 20th, 1977. Voyager 1 followed 16 days later on September 5th. The name order has nothing to do with who launched first, and everything to do with who was scheduled to arrive first. Voyager 1 rode a faster, more direct trajectory built to reach Jupiter and then Saturn quickly, using Saturn's gravity to fling itself up out of the plane of the solar system, trading away any shot at Uranus or Neptune for a close pass by Saturn's moon Titan and the quickest possible exit toward interstellar space. Voyager 2 was handed something far more ambitious. A rare planetary alignment, one that lines up Jupiter, Saturn, Uranus, and Neptune in a way that happens roughly once every 175 years. Made it possible for a single spacecraft to visit all four, using each planet's gravity to sling itself toward the next. Nobody had ever attempted a grand tour like that before. Nobody has repeated it since. To this day, Voyager 2 remains the only spacecraft in human history to have visited all four giant planets of the outer solar system. Jupiter in 1979, Saturn in 1981, Uranus in 1986, and finally Neptune in 1989. A 12-year odyssey plotted with computing power weaker than what runs a modern microwave. That achievement cost time. Every additional planet meant a longer path and a longer wait before reaching the true edge of the sun's influence. Voyager 1 crossed the heliopause, the boundary where the outward-blowing solar wind finally gives way to interstellar space in August 2012. Voyager 2 didn't reach that same kind of boundary until November 5th, 2018, more than 6 years afterward. For those 6 years, scientists had exactly one data point from beyond the edge of the solar system, and it was already forcing a rewrite of the models. But there was a catch buried inside that one data point, a detail that rarely makes it into the popular retelling, and it is the single most important reason Voyager 2's crossing mattered as much as it did. Voyager 1's plasma science instrument, the piece of hardware specifically designed to measure the temperature, density, and flow of charged particles both inside and outside the heliosphere, stopped working in 1980, not at the boundary. Not anywhere near interstellar space. In 1980, before the spacecraft had even reached Jupiter's orbit on its way out of the solar system, more than 3 decades before it would actually cross into interstellar territory. That means when Voyager 1 made its historic 2012 crossing, the one instrument built specifically to tell scientists what was actually happening to the plasma on either side of that line had already been silent for 32 years. Researchers improvised. They leaned on the cosmic ray subsystem, the magnetometer, the plasma wave subsystem, piecing together an indirect picture that was still genuinely groundbreaking, but it was assembled without the single tool that could have measured the plasma itself. Voyager 1 crossed the most consequential boundary of its mission, effectively unable to sense the very substance that boundary is made of. Voyager 2's plasma sensor never died. When it crossed the heliopause on November 5th, 2018, that instrument was still running, still functioning decades after its twin's version had gone quiet. And in that moment, it produced something that had simply never existed before. A direct, simultaneous reading of plasma on both sides of the heliopause, captured as the spacecraft physically passed through it. 5 papers, published together in Nature Astronomy in November 2019, laid out what that instrument found. And the findings did far more than echo what Voyager 1 had hinted at 6 years before. In several key respects, they contradicted it outright. The first shock was the shape of the boundary. Researchers had modeled the heliopause as a thin, sharply defined line, a transition perhaps a few 100,000 kilometers wide, where hot solar wind meets cold interstellar plasma, and the two separate cleanly. What Voyager 2 actually recorded was something far messier, a wide transitional layer, roughly 100 million miles across, sitting just outside the official boundary, where interstellar particles had already been pushing inward, blending with the outbound solar wind long before the spacecraft technically crossed the line. Voyager 1 had noticed something similar on its own approach, a stagnation region where the solar wind appeared to grind almost to a halt just inside the boundary. But Voyager 2, crossing from a completely different direction 6 years later, found a transition zone with its own distinct plasma signature. 2 spacecraft, 2 crossing points, 2 different structures at what was supposed to be the same kind of edge. Then came the distance problem, and this is the detail that genuinely rattled senior scientists on the mission. Voyager 1 crossed the heliopause at roughly 121.6 astronomical units from the Sun during a period of high solar activity. Voyager 2 crossed at roughly 119 astronomical units during a period of low solar activity, an entirely different phase of the 11-year solar cycle. Standard models predicted the heliosphere should swell and shrink meaningfully in step with the Sun's activity, ballooning outward when the Sun runs hot and pulling inward when it quiets down. Instead, both spacecraft hit the boundary at almost exactly the same distance from the Sun, regardless of what the Sun happened to be doing at the time. Stamatios Cremigis, principal investigator on the mission's low-energy charged particle instrument at the Johns Hopkins Applied Physics Laboratory, said, about as plainly as a scientist of his standing ever says something, in public that they simply do not understand why. Coming from someone who had spent decades working this data, that is not a minor admission. It means something basic about how solar activity relates to the size of the heliosphere is missing from every model built before these 2 crossings happened. The temperature findings landed just as hard. The solar wind, streaming outward from the Sun, is extremely hot in the sense plasma physicists use the word, meaning its particles are moving at tremendous speed. Scientists expected a sharp temperature drop, as that hot wind gave way to the colder interstellar medium at the heliopause, and Voyager 2 did measure a sharp drop, sharper than most models anticipated. But the number that really stood out was the temperature of the interstellar plasma itself, measured directly for the first time ever. Voyager 2's instrument clocked it between roughly 30 and 50,000 degrees Kelvin, scorching by ordinary standards, but far cooler than the tens of millions of degrees measured just inside the boundary, and notably cooler than theory had assumed. Before this crossing, that figure existed only on paper as a calculation. The direct measurement came in at roughly half what the theoretical estimate had predicted. Alongside it came density. Both spacecraft confirmed that the plasma outside the heliosphere is dramatically denser than the plasma inside it, more than 40 times denser right at the boundary. Evidence that interstellar space, far from being an empty void, is a substantial medium the Sun is constantly pressing against. The third finding, and the one Ed Stone, the Voyager project's longtime chief scientist, called the most remarkable of all, was that the heliopause leaks, not metaphorically, literally. Voyager 1, approaching from the north, had picked up what looked like fingers of interstellar material reaching inward, through the boundary before it had technically crossed. Voyager 2, coming in from a different direction entirely, detected the reverse, a trickle of low-energy particles escaping outward from inside the heliosphere into interstellar space, again before the spacecraft itself had actually crossed the line. 2 spacecraft, 2 entry points, 6 years apart, 2 different mechanisms, and the same underlying conclusion. The heliopause isn't a wall. It behaves more like a coastline, with material washing across it in both directions at once. Stone described it at the time as revealing how the Sun interacts with the material filling most of the space between stars, and the phrasing mattered. Not where the Sun's influence stops, how it keeps interacting, messily and continuously, with whatever lies beyond it. Pull back from the individual findings for a moment and think about what all of this actually says about how the mission was designed in the first place, because it's tempting to treat Voyager 2's role here as a lucky accident, and it wasn't, not entirely. When mission planners in the 1970s built a 2-spacecraft mission, working with less computing power than exists in a modern pocket calculator, they were deliberately guarding against the trap of a single data point. One spacecraft crossing one boundary tells you almost nothing about whether what it found is typical or a fluke of exactly where and when it happened to cross. 2 spacecraft, launched weeks apart, sent on very different routes, arriving at the boundary years apart from different directions, gives you the beginning of an actual picture. What those planners could not have anticipated was that the one instrument that would end up mattering most, the plasma science instrument, would fail on one spacecraft decades before it ever reached the boundary and would keep humming along on the other all the way through. The division of labor was intentional. The specific way it played out, with Voyager 2 quietly ending up as the sole source of direct interstellar plasma measurements, was not something anyone designed for in 1977. It's simply what happened. And it's what turned Voyager 2, the twin, the second name, the spacecraft people mention almost as an afterthought, into the single most important source of direct interstellar plasma data humanity currently has. Which brings everything to right now, to the summer of 2026, and to the reason Voyager 2 has suddenly become the focus of attention at the Jet Propulsion Laboratory again. Both spacecraft run on radioisotope thermoelectric generators, devices that turn the heat given off by decaying plutonium-238 into electricity. At launch, each one had roughly 470 watts to work with. That number has been sliding ever since, losing around 4 watts a year as the plutonium decays, a slow, mathematically certain countdown with no way to pause it, reverse it, or refuel it. There's no adding power back to either spacecraft. There's only the question of how efficiently what remains can be used and how long engineers can keep stretching a shrinking budget across whichever instruments are still worth running. Voyager 2 currently has 3 working science instruments left. The plasma science instrument, the very one that made the 2018 crossing so significant, plus the magnetometer and the plasma wave subsystem. Voyager 1, meanwhile, is down to 2 after its low-energy charged particle instrument, LECP, was switched off in April 2026 to buy time. Voyager 2's own LECP had already gone dark back in March 2025 for the same reason. The procedure now underway is the boldest power move either spacecraft has attempted, and the team's nickname for it, the Big Bang, is not for show. Instead of making small changes one at a time, verifying each before moving to the next, the plan calls for swapping out a whole cluster of power systems at once. Some things get switched off, others get replaced with lower power alternatives. The way power flows through everything still running gets reorganized in a single coordinated operation, executed simultaneously rather than gradually. The logic is almost backwards from what you'd expect. A slower, step-by-step approach would spend more time sitting in half-finished, unstable configurations, and those in-between states are exactly what tends to trip the spacecraft's automated fault protection, the built-in safety system that starts shutting components down on its own the instant it senses power demand, outpacing what the aging generators can supply. Doing everything at once is meant to blow through that dangerous transition as fast as possible. And there's no room to try again if it doesn't go cleanly. Every command sent to Voyager 2 right now takes upward of 16 hours just to arrive. Every confirmation that it worked takes another 16 plus hours to come back. A single round of troubleshooting eats well over a full day. And there's no way to pause mid-maneuver and simply retry next week. This is a single-shot operation, run across a communication delay that makes any kind of real-time correction impossible. Voyager 2 is going first, and the reasoning is straightforward once you see it. Not because it matters less than its twin, but because it currently sits closer to Earth, roughly 13 billion miles compared to Voyager 1's roughly 16 billion, and because it still has a slightly larger power margin to work with. That makes it the safer place to test something this drastic before attempting the same maneuver on the far more power-constrained Voyager 1. An attempt expected no earlier than July of this year. If the Big Bang works on Voyager 2, engineers believe it could buy at least another year of instrument operation, possibly more. If it succeeds again on Voyager 1, there's a real chance the recently shut down LECP could be switched back on, since engineers deliberately left a tiny half-watt motor inside it running, just in case that door stays open. If either attempt fails, there's no fallback plan waiting in reserve. The spacecraft either settles into a new, more sustainable configuration, or it doesn't, and whatever power cushion existed going in is simply gone. What's actually at stake here is bigger than the survival of 2 aging machines. The 5 Nature Astronomy papers from 2019 raised as many questions as they resolved, and every one of those questions currently has exactly one active source of new data capable of chipping away at it, and that source is these same 2 spacecraft. Why does the heliopause sit at nearly the same distance from the sun, no matter where things stand in the solar cycle, when the models say it shouldn't? What actually drives the leakiness of the boundary, and does the rate of that leak shift over time as the sun continues drifting through different pockets of the galaxy's interstellar medium? What is the true overall shape of the heliosphere? Still a genuinely open question, with some models predicting a long cometary tail trailing behind the solar system's motion through the galaxy, and others suggesting something closer to spherical or even lopsided. Voyager 1 and Voyager 2 sample. Exactly 2 points on that structure, one closer to what would be the nose, one closer to the flank, and every additional year either spacecraft stays alive adds one more data point to a picture currently built on just 2. Underneath all of it sits a harder truth. There is no third spacecraft out there. There is no follow-on mission currently funded, designed, or approved to pick up where either Voyager leaves off. Whatever these two machines are still able to measure right now in 2026 is effectively the only real-time, in situ data humanity has from beyond the edge of the solar system, and it's likely to stay that way for decades. Once the last working instrument on the last surviving Voyager finally goes dark, the map simply stops updating. Every question the 2019 papers left open just sits there, unanswered, until some future mission, not yet built, not yet funded, eventually makes the same decades-long journey and reaches the same boundary from scratch. It's easy to get lost in the sheer scale of Voyager 2's resume. The only spacecraft ever to visit Uranus, where its 1986 flyby turned up 10 previously unknown moons, 2 new rings, an axial tilt of almost 98 degrees, and a magnetic field so strangely misaligned with the planet's own rotation that it still complicates theories of how planetary magnetic fields form. The only spacecraft ever to visit Neptune, where its 1989 flyby, the final planetary encounter of the whole Voyager program, discovered 6 new moons, including one large enough that it arguably should have been spotted from Earth long before Voyager got there, clocked supersonic. Winds faster than anything else measured in the solar system, and caught active nitrogen geysers erupting off the surface of Neptune's largest moon, Triton, a world almost certainly captured from the Kuiper Belt rather than formed where it now sits. A 14th moon found at Jupiter, confirmation of the active volcanism on Io that its twin had spotted first. Images of Europa's fractured icy shell that helped seed decades of scientific curiosity about a possible liquid ocean beneath the surface, curiosity that eventually led to the Europa Clipper mission now underway. All of it from a spacecraft launched in August 1977, built with technology that predates the internet, GPS, and the personal computer, as a household item designed for a mission expected to last 4 years. But the achievement that matters most right now in the summer of 2026 isn't any of the planetary flybys. It's the fact that one instrument, sealed inside a spacecraft roughly the size of a small car, and now limping along on a sliver of its original power, kept working long enough to hand humanity its first, and so far only, direct measurement of what interstellar plasma actually is, taken from inside interstellar space itself. Voyager 1 got there first, and it will always be remembered for that. Voyager 2 is the one that could actually tell us what was waiting when it arrived. Right now, a small team of engineers at JPL, carrying institutional knowledge about spacecraft systems that mostly doesn't exist anywhere else anymore, is running the big bang tests on Voyager 2, sending commands across 13 billion miles of empty space and waiting more than 16 hours just to find out whether the last one worked. Whatever happens next, whether the maneuver succeeds and buys Voyager 2 another year or more of science, or something goes wrong in a transition state that fault protection can't pull it back from, the outcome will directly shape what NASA is willing to attempt on Voyager 1 later this summer. 2 machines, built in the 1970s, still cutting through the dark between the stars at 34,000 miles an hour, still sending back a signal that takes 16 hours to arrive and tells us more clearly than any model ever managed that the edge of our solar system isn't a wall, it's a coastline. And for now, against every original expectation about how long either of them was supposed to last, the surf is still running in both directions. If you want to know what NASA finds when the Big Bang results come back from Voyager 2, and what that means for the attempt on Voyager 1 later this summer, subscribe and turn on notifications. Because when that signal finally arrives, you'll want to already understand exactly what you're looking at.